All right, well, good afternoon, everyone. I want to thank everyone for joining us today. I'm here joined by a couple of colleagues, Sean Maurer and Cassie Carroll from the Smart Energy Design Assistance Center. Also have the pleasure of being joined by Jackie Christensen from the Urbana-Champaign Sanitary District. Today we're going to be looking at energy regarding phosphorus and nitrogen removal strategies, and today's session will last approximately 1 hour. As far as controls, if you hover your mouse towards the top or bottom of your screen, you should have a control panel up here with options. Feel free to go ahead and use the question and answer function for any questions that you may end up with during this session. We may answer those as we go along or towards the end. So if you do go ahead and put those questions into the Q&A box, that would be wonderful. If you do put them into the chat, we may or may not see those. So today's presentation is being recorded and will be posted to our website, sedac.org. So if you end up having other colleagues or miss something and want to go back and review it, feel free to go take a look at those archive versions. As far as certificates, everyone attending today will receive a certificate of participation. We are still working on getting the course number for that, but that certificate will be usable for your professional development hours for both operators and engineers. So also want to make everyone aware that this is the second in a series of webinars. Our last webinar was on lift stations, and the next webinar coming up in the series is on November 17th. And that is covering optimizing wastewater treatment operations through data and analysis technologies. With that, let's go ahead and get started along. On our next slide here. Here at SEDAC, we are here to assist buildings and communities in their goal of reducing their energy footprint, with our goal of reducing the energy footprint across the state of Illinois. So some of these trainings are one of the ways that we do that. We are part of a public-private partnership between the University of Illinois and 360 Energy Group. So they are our partner firm. Something that is available for all publicly owned wastewater treatment facilities is SEDAC is partnered with the IEPA along with the Illinois Sustainable Technology Center to provide no-cost energy assessments. So these are being funded in part by the IEPA and the State Energy Office. And so as part of these, we do provide a detailed assessment report, including opportunities and payback analyses. We've had several plants take advantage of these opportunities and use them for several different things. Some facilities already have some projects in mind and want assistance as far as helping to quantify what the savings opportunity and payback is. And others have been approached by outside firms looking to provide some assistance and looking for some third-party verification as far as are these really real savings numbers or perhaps things to be aware of as looking to implement some of these. We do have several online resources at our website here, smartenergy.illinois.edu/wastewater. Some of those resources do include archives of these webinars, along with other information, and that's one way to apply for the no-cost wastewater treatment plant assessment. And so this is open to all wastewater treatment systems, whether you are a lagoon system or a aerobic or anaerobic digestion, or whatever your wastewater process is. This is open to you for publicly owned assessments. So touching a little bit on upcoming regulations, what we're seeing here is one of the reasons why phosphorus has really come into the fold here for regulations is we're seeing a lot of growth in bodies of water, and understanding that while wastewater treatment facilities originally were designed for nitrogen removal and did a very good job at that, phosphorus has come into the fold going into the future. So this is part of some of the nutrient standards that Illinois has adopted in conjunction with the US EPA. While the US EPA had recognized and developed some of these standards, and then Illinois has adopted and modified them to fit our needs here in the state of Illinois. So the primary goal is to get a 45% reduction in nitrogen and phosphorus. This includes both point sources and non-point sources, with some interim goals set by 2025. One thing that was noted as part of these, there is a report and monitoring done as far as interim along the way to see how we're doing in this. And the most recent report done in 2019 using, I believe, 2018 data was showing that we've really made a good stride as far as our phosphorus reduction and have already nearly met our 2025 target. So nitrogen, we are still making good progress. 10% on the way to our 15% goal. So here we are using 2018 data. You know, we're just into this not even 5 years, and so having some very good success with this. So as I noted earlier, many facilities already do very effective nitrogen removal. That was, as many of these processes were originally designed, was for nitrogen removal. And so the focus now is turning towards phosphorus reductions, particularly at major wastewater treatment facilities, those that are over 1 mgd. And recognizing that those that are over 1 mgd are providing the majority of where the phosphorus is coming from. Those that are minor plants under 1 mgd are fairly minor sources in the overall grand scheme of things. So they're also working on studies as far as trying to, anytime a facility is looking to build a new facility or expanding plants, or they are modifying plants that do discharge into impaired waters, that is definitely when phosphorus regulations are going to be looked at for any permitting. And with the goal here that plants need to develop plans to achieve phosphorus limits of 0.5 milligram per liter or lower. Previously, this was upwards of 1 milligram per liter. Fortunately, so far, we have not had to go to the much more stringent 1/10 of a milligram per liter. And so here with these charts illustrating that and recognizing that point sources such as wastewater treatment facilities have done a very good job as far as controlling nitrogen, whereas phosphorus has not been as aggressive as far as the design goes. And also recognizing that agriculture is really playing a large role in all of this. And so with the 45% reduction, this is also focusing on a 45% reduction, not only from point sources as wastewater treatment facilities, but also for agricultural purposes as well. So, uh, recognizing that nitrification and denitrification is part of our nutrient removal, these can be done as two separate processes, but if they are able to be done in a single process, generally that leads to a much lower energy uh, footprint, as well as a smaller plant physical footprint. Uh, and so phosphorus, we see the chemical removal through chemical additions is more commonly used. And particularly this is for struvite formation to make sure that we're precipitating phosphorus where we want it to be, and not that it just happens to fall out inside of our equipment where we may not want it to be. So biological phosphorus removal, which Jackie's going to talk a little bit more about their experience at the Urbana-Champaign Sanitary District. This is a multi-step process and looks to promote the growth of phosphorus phosphorus hungry organisms. And so those are looking to control phosphorus through biological means. So with that, I'm going to turn it over to my colleague Sean Maurer to talk about some of the various process opportunities and their energy impact.
Thank you very much, Ryan. So I wanted to just go through briefly some of the different phosphorus and nitrogen removal strategies and their energy impacts for plants. One of the most common ways for phosphorus removal, as Ryan noted, is chemical removal. You're looking to precipitate phosphorus out by adding a chemical salt that the phosphorus will bind to. It becomes heavier, and then it can settle out in either a filtration system, or it can settle out in a secondary clarifier or tertiary clarifier. And usually this is a very low energy process means to do it. Mostly because you're adding a chemical. You just got the small dosing pumps. You may have a storage building that you need to store those chemicals in, that may have heating and cooling equipment, just to make sure that those chemicals are stored at appropriate storage temperatures. But overall, that's the extent of the addition of energy, unless you're using a filtration system, in which case you've got backwash energy for the filters. But a lot of plants that use a filtration strategy already have filters in place, so it's not an additional energy penalty for them. It's a very reliable means to getting low phosphorus results. Those chemicals are generally a stable means to remove phosphorus, whereas a biological process is susceptible to changes in your influent water. Any kind of chemicals that might be in there could disrupt that process. So it's a little more difficult to use a biological process than a chemical one. And that's why these chemical additives have been more popular in recent times. On the downside, though, it does increase the phosphorus in your sludge. So you do have an increased sludge volume you now have to handle. And it does have an impact on the dewaterability of that sludge. So you've got, on top of more sludge production, you've also got a higher water weight in that sludge. So some of the things to consider when you're looking at a chemical means to remove phosphorus. Again, it's going to be an almost guaranteed way to hit a higher restriction, hitting those targets of 0.5 milligrams per liter. But you do have some impacts on other waste streams, such as solids handling, to be aware of. We do have a lot of clients that have lagoons, and there are options for lagoons to add additional nitrogen and phosphorus removal strategies. Lagoons can enhance nitrification and denitrification by adding anoxic and aerobic zones to an existing lagoon aeration system. You can see a diagram here on the top right corner. They've broken this lagoon up into multiple sections with some hanging separators, some separator curtains, um, and they've changed the aeration pattern within each zone to set up a zone where you can do nitrification and denitrification processes. For a lot of lagoons, to do an enhanced biological nutrient removal is going to be an increase in energy consumption. So what you want to look for is how to minimize that additional energy in that process. Um, you're going to have some additional energy by using it. You're going to minimize that additional energy by using existing lagoon as much as possible. So you want to try to, if you can, avoid adding external processing tanks. But that is a common process for handling phosphorus, is adding in an anaerobic tank outside the lagoon um, on the inlet side, um, doing that anaerobic processing that promotes the growth of phosphorus absorbing organisms, um, and then letting that feed into the lagoon for nitrification and denitrification. If you can set up the lagoon itself with an anaerobic zone and an inlet, and then have a divider curtain that then separates that lagoon section off. Um, you limit the additional land area you need, and you limit how much energy consumption you'll have for that process as far as pumping and recycle. Um, Again, noting avoiding the external tanks and clarifiers added onto that lagoon, as that will increase the pumping energy required. Anytime you're going to do enhanced biological nutrient removal, you're going to have recycle streams, return activated sludge added to that process. So if you can avoid adding additional tanks and stuff and just recycle within a lagoon basin, you're reducing the head pressure and reducing the pump size, so you reduce the overall energy consumption. Lagoons that do not have aeration and mixing already will generally have to add some in order to support the biomass needed to do enhanced biological nutrient removal. So if you've got a facultative lagoon or a partially mixed lagoon, more than likely you're going to have to add an aeration system or mixing system in order to support the microbial life needed to do enhanced removal strategies. For an existing activated sludge plant, a lot of plants we're already seeing are modifying their aeration basins to add in a anoxic zone, and that then feeds into an aerobic zone, and that's for nitrification denitrification purposes. We've seen a few plants that have added in an anaerobic zone first in order to start growing those phosphorus absorbing organisms. Um, so you can take an existing aeration basin um, and separate it into those three basin types: an anaerobic basin, an anoxic basin, and then an aerobic basin. Um, Usually you'll be able to remove nutrients and you'll be able to increase the processing capacity of your plant. Um, your mixed liquor suspended solids rate is going to go up. Again, that's in order to support that biological process. Um, but you're going to not have to add additional basins and tanks in order to add those processing streams. You're not going to have to then support um, external recycle pumps and pumping between different basins. You can recycle within the same basin, and again, you're limiting that head pressure requirement, so you're limiting the additional pumping energy. And when you take a fully aerobic basin and break it down into an anaerobic portion and an anoxic portion, those both require less aeration. So you can get significant aeration savings from a process like this, increase your processing capacity slightly, and then you do have a little bit of trade-off with that recycle pumping energy in order to maintain the microbes that you need in the system and your mixed liquor levels. But overall, it nets a positive energy savings from reducing that aeration amount. Some other processes, you can add side stream processing to existing plants that already have a nitrification and denitrification process train in order to remove phosphorus. We've actually see this very commonly with plants that already have an anaerobic digester. Supernatant from that digester can be put into an anaerobic basin. Influent comes into that has the carbon load needed to grow phosphorus absorbing organisms, and that promotes their growth. And then that feeds back into their existing nitrification and denitrification process. So with the addition of one additional tank, plugging that into a recycle loop that's already there for the supernatant process, you can minimize the energy impact for removing phosphorus for a plant that is already meeting their denitrification targets. Um, Also, there are side streams where you can do chemical addition and settle out phosphorus into a separate clarifier. Um, the purpose there is to limit the impact of solids dewatering. That additional phosphorus salt, that struvite, that makes dewatering more difficult for your dewatering process. If you can separate that from your standard sludge, then you can handle that separately and limit the impact of that on your sludge handling process. But what about for new construction, or if you're having a plant that's doing a major renovation and kind of changing the process out altogether? You want to focus on maximizing the use of gravity through the plant and reducing recycling as much as possible. Um, Again, that's where your biggest energy penalty comes from doing enhanced biological nutrient removal, are those recycle streams that are necessary. You'll have generally a recycle stream coming from the end of your aerobic zone feeding back into your anoxic zone, and usually the end of the anoxic zone feeds back into the head of the anaerobic zone. And the reason that's done is to reduce the possibility of having oxygen feed into your anaerobic zone and disrupting the anaerobic processes. You wouldn't want to send recycle from the end of your aerobic zone where you've got higher DO levels into the anaerobic portion and disrupt that process. So usually there's those two recycle streams that are added in for new construction plants or existing plants that have a significant energy penalty. Um, Integrated film activated sludge systems are a good option for simultaneous nitrification and denitrification. They support a larger biomass and have a greater nutrient removal per gallon because of that higher biomass. They're also more resilient against washout during higher flows because your biomass is adhered to a substrate, so it can't just flow out in the effluent stream. Um, and also because of that higher biomass, they're also more resilient against any chemicals or things that might disrupt the process coming in the influent flow. Just because of the greater biomass, there's more likelihood that they'll survive. You won't have enough of that biomass die off from a chemical influx as you would in a lesser density biomass system. Simultaneous nitrification and denitrification relies on the addition of ammonia sensors to a DO sensor. So there is a little more control complexity there. Um, but a lot of times that automation, you're adding in that ammonia sensor. Um, it's not a significant addition as far as complexity to the process. It's usually fairly simple and straightforward to tie into an existing SCADA system. Just takes a little work with an engineering staff to figure out what the set points need to be for your process to handle that denitrification load. And also eliminating the need for recycle from anoxic to aerobic to control nitrates by having that ammonia sensor added. So you can save a little bit of energy. Usually you've got recycle from the end of your aerobic system back to the head of your anoxic system because of with just DO control, you don't have an exact measurement of the total nitrogen in that system. So there's recycle back through the system to maintain the microbe levels and to maintain a food source at a proper level to prevent disruption to the process. Once you add in that ammonia sensor, you can control more specifically your aeration process. Um, it results in slightly lower DO set points in that aerobic section. Um, and so that then eliminates the need to have that recycle stream and can eliminate that additional energy consumption for your plant. So what we've seen kind of on the top right corner here is a chart of some cost savings. Um, just an example plant that had a simultaneous nitrification denitrification process added that also had ammonia control. And you can see their airflow reduction from about 8,000 CFM down to 3,000 CFM, and they achieved about $150,000 per year in cost savings from having that additional control and reducing their aeration energy. So what different processes are out there? What should you look at for your particular plant? Um, there are a lot of different options out there. A lot of them are modifications of each other. The one that we see probably most common at a lot of plants in Illinois is the modified Ludsack-Ettinger, or the MLE process. We also see that modified process set up in an oxidation ditch. Essentially, you have a pre-anoxic basin, which is a low oxygen basin that's promoting uh, early nitrification, um, if I have that right. Um, and then that's followed by an aerobic basin, um, followed by a clarifier to settle out your biomass in the stream. And you have recycle from the end of that aerobic stream back to the head of your anoxic basin. Um, in order to modify that MLE process to handle phosphorus, you can add an anaerobic basin, which is a zero oxygen environment. I know we just had a question come in about the difference between an anaerobic and an anoxic zone. The anaerobic zone has no oxygen in it at all, um, whereas an anoxic zone has a little bit of oxygen addition, but you're mainly relying on oxygen bound to nitrogen molecules, um, so that you can it's part of the denitrification process. Um, the oxygen that's bound to the nitrogen gets used. Um, nitrogen gas then is off-gassed, and then microbes use that oxygen for growth and energy, and converting nitrates into nitrites. And we're getting the chemicals correct there. And similarly for an oxidation ditch, um, they are particularly well set up for an MLE type process, as they already have an oxygen gradient set up. You have a high oxygen content right by the surface aerators, usually some kind of rotor system, or maybe a subsurface mounted propeller type aerator. And then as you move away from that, you get into a anoxic type zone, kind of shown in the diagram there. So they're already set up to be used as a kind of an MLE process. Um, Again, if you want to do phosphorus removal with a process like that, usually it's done with chemical addition afterwards with subsequent filtration or settling out in a clarifier. But you could also do an anaerobic basin ahead of that oxidation ditch and add that anaerobic stream right at one of your aerators to make sure that it gets oxygenated properly, um, and then move that through the process. Um, Probably the most common throughout the US is the A2O process, as far as plants that have phosphorus removal already in their stream. It's a modification of the MLE process where you have the anaerobic basin, then the anoxic basin, and then your aerobic basin. Um, it's a fairly good process for phosphorus and nitrogen removal. Since a lot of plants are already familiar with an activated sludge process, it's only a minor modification from that, so it's easy for operators to understand. The Cape Town process is a little more complex, but again, it's kind of a modification of the MLE process with a little more recycle, um, trying to stabilize your oxygen levels that are being recycled into each section of your anaerobic, aerobic, and anoxic sections of the system. It's trying to provide a little more stability to the process with more recycle streams. But because of that, it's a little more complex, a little more expensive, but it does get a much better nitrogen removal and phosphorus removal than some of the other processes. One that we've seen kind of growing a lot for phosphorus removal particularly is sequence batch reactors, because you can tune that sequence in order to hit specific targets for nutrient removal. It's mainly just adjusting the timing of that process with some additional sensors for ammonia and phosphorus in the stream to detect whether you're hitting your targets or not. Really, it's just changing the different processes timing in order to get better removal. So if you've already got a sequence batch reactor process at your plant, it's fairly straightforward to modify to get to that. However, if you're building a new plant, it is a highly expensive process since you're adding a lot of controls. There's a lot of weir gates and things that need to be properly controlled. There's a lot of sensors to it. So it's a high cost to install initially. But once you get it up and running, it's a fairly low cost overall to operate long term. And one of the things we wanted to point out is for the lagoon operators out there, you can use chemical addition to get very good phosphorus removal with some minor modifications to your existing lagoons as far as breaking up into separate basins with an existing lagoon. You can get pretty decent nitrogen removal. We do note that because of the energy cost for a lagoon as far as dollars per million gallons treated, lagoons tend to, for enhanced biological nutrient removal, tend to be a higher energy consumption per million gallons, even though overall, just due to their size, they are lower energy than some of these other plants in total. They are a higher energy per million gallons. For any of these processes, you can add in a fixed film type system to improve the stability of your process. The integrated fixed film can reduce your energy consumption overall, mainly because you're aerating a larger biomass in a smaller basin. So you're saving a little bit on aeration, as you don't have to spread out over, you're not aerating just the fluid, you're aerating directly the biomass. And you're also reducing your recycle energy in that process. So it can increase your nitrogen and phosphorus removal potential while decreasing your overall energy consumption. But what I'd like to do now is let Jackie Christensen discuss a little bit about what Urbana-Champaign Sanitary District did with their plant. Jackie began her wastewater career with Richmond Sanitary District in Richmond, Indiana. Started as a lab technician and advanced to assistant director. After relocating to Champaign, she worked in the private sector as an environmental manager for Guardian West, an automotive parts manufacturer. The move back to municipal wastewater occurred in 2007 with employment with UCSD. She became the director of operations in 2010. She has a Bachelor of Science in Biology from Ball State University in Muncie, Indiana, and a Master of Science in Hazardous and Waste Materials Management from Southern Methodist University in Dallas, Texas. So Jackie, I will let you take over.
All right, thank you. So if you're familiar with Urbana-Champaign Sanitary District, we do have 2 treatment plants. And the smaller plant, which is the Southwest plant, is more advanced on the nutrient removal. So I wanted to concentrate on that because if you start talking 2 plants at once, it can get a little confusing. So slide control. Sean or Ryan? Oh, there we go. Okay. So the Southwest plant, the original plant, was built in the late 60s. And as typical with a lot of treatment plants, you have small and large different construction projects. So from the 60s to about 80s, it was, pretty much just a typical plant. And in the 80s, some of the regulations changed. The ammonia limits came in a little bit tighter, and it was also required to do phosphorus removal. So nitrification towers were added after the activated sludge basins. And keep in mind that the nitrification towers, which is a fixed film treatment, is only meant to convert ammonia. It's really not meant for total nitrogen removal. So in the 80s, we also went with chemical feed for total phosphorus control. The limit was 1 milligram per liter, and we actually had a 2 milligram per liter daily limit, which was a little unusual, but with our downstream situation, basically we are the stream, and then there is a Lake Shelbyville under or below us downstream. So things pretty much stayed the same until 2005 with some of the upgrade, which was a large upgrade. We converted from the ferric feed for total phosphorus to a biological. The process that was selected was an AO. It's very simple. It was one of the first ones in Illinois, so it was built with a lot of, it was overbuilt a little bit with detention times because it hadn't been proved out in Illinois. So the AO process combined with the nitrification towers, which remained, were how we addressed the nutrient issues. The total phosphorus limit remained at 1 milligram per liter until just recently in the 2019 permit. In 2019, the new permit, that 1 milligram per liter concentration has been dropped to 0.5 milligram per liter. But instead of a geometric it is now an annual geometric mean calculation. So there is a difference between a monthly average and an annual geometric mean. It gives you a little bit more freedom to have a couple of higher days and still meet an annual average. Okay, next slide. So just an overview of the Southwest plant. So on the right side of your screen, the raw sewage comes into the headworks, and then where the red and the blue arrows divide, that is the flow control for main plant versus excess flow. So typically you would follow the blue lines, which would take from headworks to your flow control and into your activated sludge and BioP. One thing that you'll notice about this plant is it does not have primary clarifiers. So without the primary clarifiers, it does change the game a little bit. And I think that's why they could go with such a simplified process, just a straight AO. So after the activated sludge and BioP, then we have 5 secondary clarifiers. The flow goes into the 2 nitrification towers. The underflow then goes to, we do have tertiary filtration. It is the cloth filter disc. Then the flow goes to old chlorine contact tank, which currently is not used. We've had a chlorine exemption for a while. And then would combine, if we were having excess flow, it would combine with excess flow and then discharge to the creek. Okay. So just zeroing in a little bit on the actual activated sludge. So the raw, it's basically screened raw influent, mixes with the return sludge on the far left-hand channel, comes up to the north side or the top of the picture, and then goes down through 2 of the anaerobic tanks. Those are just mixed with low energy 5 horsepower mixers. There are 8 total of those. And then when the the flow reaches the south side or the bottom of the picture, then it divides and goes in the opposite directions through the 5 remaining aerobic basins. So we have the 8 horsepower mixers in the anaerobic, and then we do have the fine bubble for aeration. So this is where, this heart of the, BOD, suspended solids, treatment, total phosphorus. And then we go into the nitrification towers. And if you've not seen one of these before, basically, you probably won't see this variety ever again. The bottom part of the tower is basically a storage room. And I'll touch on that a little bit. But you can see where the handrail is. Everything below that's just empty storage. The media actually starts at the handrail on up. So the next slide will show you what the media itself looks like on the distribution system. This is all driven hydraulically by the pumps underneath. So we're pumping water up into the distribution arms, and that is what is driving the arms around, sprinkling the water on top of the mix or the fixed film media. So you have growth on there. You'll get an algae growth on the top surface, but underneath you'll have a mixed variety of different films and microorganisms. There is some maintenance with this, as far as occasionally you'll go in and you'll have an overgrowth of algae on the top of the surface, and you'll get ponding. So we'll take the tower off either in the winter and basically freeze dry the algae off of it, or we can also take it off in the summer and just let the sun bake it and kill that top algae, and then it'll flush through. So anytime you talk about a plant, you always want to know, well, what kind of limits do they have? So our 2005 limits, when we first did the conversion to the BioP, you can see we had a 1 milligram for total phosphorus, BMD and suspended solids, pretty typical. And then we have warm weather ammonia limits and cold weather ammonia limits. The 2019, we did see a reduction in our limits. Total phosphorus, we did drop down to the 0.5, but it's a little different calculation. And then the ammonia limits dropped some. They weren't too dramatic. And one of the things that we were really concerned about was a total nitrogen limit, which was not included in the 2019 permit renewal. So this is just an indication of what's going to happen in the future, which will be the limits are always going to be dropping. So the plant itself, performance-wise, you can just did a summation for 2019. We have very good effluent, really good removal, unless you look at total nitrogen. We don't currently have a limit, but some of the numbers that have been thrown around are maybe a total nitrogen of 10, maybe 8. As you can see, we would not make that kind of limit at this time. But we do well on all the other parameters. So some of the energy considerations, and I want to come back to the tower and why I said you'd never see those again. 24 feet of that tower, of that 70-foot tower, is nothing but a storage room. So you've added 24 feet of total dynamic head on those pumps, on the energy demand off those pumps. We have 3 150 horsepower pumps, but they are on VFDs. They're a little different. They're magnet drives, which is a magnet actually controls the distance between the two magnetic plates. And as the plates distance increases, it slows the pumps down. So they are a little unique. Not a lot of people have those magnet drives. When we installed, or when we converted to the BioP from the chemical edition, it did take about 3 months to do that conversions, to grow up the PAOs sufficiently that we were within the compliance limit of 1. One of the other energy considerations to take into account is, okay, 2 out of the 7 basins now aren't being fed by the blowers, so you think you have a dramatic drop, but you are adding, some horsepower demand by adding mixers. How much mixing is required is a little plant specific, depends upon where you're running your mixed liquors. Out of the 8 mixers, we know we can survive without 1. If we lose 2, we're going to have a problem with our phosphorus. Okay. So I ran the just our energy use. Keep in mind that all the major pumps out at Southwest do have VFG drives on them, so that helps. The blowers are 250 horsepower. They are single stage centrifugal blowers. We only really need to run one at a time. So that does help when we do the controls by our DO set points within the aeration basins. Looking at the actual electrical use and cost, and don't ask me why the dip in March of 2020. After I sent the slides in, I started looking at that. I probably need to look at that power bill a little closer, because that is an unusual thing to have that kind of power dip. But basically, we're spending $25,000 a month on electricity at Southwest plant. It's about 375,000 kilowatts per hour per month. And if you've looked, we're paying about 6 cents a kilowatt hour. If you've ever looked at your power bills, they are a little hard to read. When you start looking, it's like, wow, I'm only paying 6 cents. But when you start looking at your power demand charges, your carrier charges, there's a lot of things that are not in your control. And when you start trying to equate, well, if I drop 100, say I drop 20,000 kilowatt an hour, it's going to equal a certain amount. Well, yes and no, because it depends upon what's happened with your demand charge and some other things. And maybe Ryan can talk a little bit more about that, or Sean, because they've had a lot of experience looking at those power bills. We also did an audit with SEDAC. It was very useful, and we did, and I know that's one of the things that they looked at. So looking at the future for us, one of the big things we're going to have to think about is the plastic media and the nitrification towers do have a shelf life. And typically they say 15 to 20 years. We're working on 35 now. So if we are going to keep those as a major part of our ammonia control, we're faced with probably about $2 million expenditures just to keep that process going. One of the other things we're going to have to do is re-rate that plant pretty soon. Urbana-Champaign is changing a little bit. We've been noticing that we're losing flow at the Northeast plant, which is supposed to be the larger of the two, and we're gaining flow at the Southwest. And we're not quite sure when that's going to equate, but my prediction is that the two plants are going to be the same size probably within 10 to 15 years. So we're already seeing we're getting closer to our rated capacity. Some of the other things we're going to look at, we are in a long-range facility plan evaluation, and how are we going to handle the future regulations? What happens if they do put in total nitrogen? We can't do it with our current setup. Phosphorus, I think we're in good shape for a while, unless they do drop down to 0.1, and I'm pretty sure we can't make it with our BioP. It's pretty steady. It's not easily upset, but we're always hanging around there, about 0.25, 0.3, 0.35 on our effluent concentration. And then, as I mentioned, we're wasting 25 foot of TDH of empty space just to pump above an empty garage on those nitrification towers. So what can we do if we're going to keep that system? So there's a lot of questions for us in the future too, just like the rest of everybody. What are the rules going to be, and how are we going to meet them? So that's basically, I just wanted to give you an overview of what we've done in the past, and we're in the same boat as everybody else, just trying to figure out where do we go from here.
Thank you very much, Jackie. Appreciate it.
Welcome.
We'd like to open it up now at the last few minutes of our presentation. If there are any questions that you've had that maybe we didn't get to answer in the presentation, if you saw something you're not quite clear on and want further clarification, or if you want to ask Jackie some questions about their process, we'd just like to open it up to everyone else now to ask a few questions. Mary Dressel, Jackie, I think this might be for you. Asks, how often do you run total phosphorus testing?
The operators do a grab sample every day, and they're out there 5 days a week. For permit testing, it's 2 days a week.
Okay, thank you. Ryan, did you want to touch on demand charges and energy?
Sure. Sure. As Jackie noted, there are two different components. You have an energy charge, and then commonly for facilities, you will also have a delivery charge for electricity. Larger facilities frequently do have demand based charges. Smaller plants will have consumption based charges. A good way to relate to that is a demand charge is based on your highest peak during the month, or what was the largest pipe I needed to serve you during that month, whereas a consumption is the flow through the pipe. So as Jackie kind of alluded to, for them, modifying if they're able to save 20,000 kilowatt hours a month, that will save on their energy charge, but it may not save them on delivery charge because their delivery is going to be based on when that savings occurred. And if you can, rather than having peaks and valleys, if you can push those peaks down, you can really save on some of that delivery charge. So, we've seen commonly for those that are on a demand-based charge, delivery rates can be somewhere in the 30 to 50% range, but that's normally for larger plants or plants perhaps in the ComEd territory. I believe most ComEd is in on demand-based rate for delivery.
We did get a question on where is the best location for chemical addition for phosphorus removal in a conventional activated plant. Primarily that's going to be where you're doing your settling of solids. So your primary clarifier, if you got secondary clarifiers or secondary or tertiary filtration, that's where you're going to want to do your chemical addition so you can settle out that phosphorus in a place where you've got the equipment to handle that solids settling out. you don't want to do that addition right before your aeration stream, because you're going to be depositing struvite stuff then in your aeration basin. You don't want to have that kind of buildup. So your chemical addition should be at your filtration and your clarification stages of your process. I did just want to touch on again, we did get a question earlier on the difference between an anaerobic and an anoxic zone. Just to make sure that distinction is clear. An anaerobic zone, you're not adding any aeration to that basin. It's completely devoid of oxygen. An anoxic zone, you're adding a little bit of aeration, but you're primarily relying on bound oxygen with your nitrogen molecules. Um, and so um, it's limited aeration in that type of basin, and then an aerobic basin is full aeration with a DO set point, usually somewhere around 2 milligrams per liter. We did get a question, is there a copy of the lift station webinar that could be watched? There should be a link on our website. If you go to SEDAC.org, or there, that should take you to our website. In the top of that page, you can find a link to our wastewater page, and that should be listed at our wastewater page. And we have a question for Jackie. Do the tertiary filters also assist with phosphorus removal? And if so, is it a significant reduction?
We've had some issues when we take the nitrification tower offline and dry it out, you put it back online, it's going to slough off a lot of that organic material. And we'll see loading on the filters. We'll have shortened backwash times. And those filters do rip, they get holes in them, and you can blow solids through them. And if we're having a higher effluent suspended solids after the filter, our phosphorus does seem to go up with it. So there is phosphorus that's in those biological solids, and if they do get through the filters, we will see it in the effluent.
Yeah, in general, anytime you've got a low oxygen environment or close to anaerobic environment, which tends to build up on filters as you get a thicker mass on that filter media, you'll start to get some PAO activity and growth there that will do some phosphorus removal. How will this be implemented in small towns with lagoon operation? So probably I would expect with regulations, the focus for small towns and lagoons is going to be on nitrogen, because as noted by Ryan early in our presentation, they're a small component of the phosphorus addition overall to the system. But if lagoons do end up having phosphorus limits, they'll probably be at the 1 milligram per liter or half milligram per liter, where larger plants will have that half milligram per liter or 0.1 milligram per liter. And most lagoons, I would think, would probably go with a chemical addition in a settling basin or a rock filter of some sort to capture that phosphorus and struvite settling. I don't expect too many lagoons are going to do a full modification in order to do biological phosphorus removal.
And that has been acknowledged by the IEPA that small plants do tend to have challenges, which is primary reason why they do have that distinction between that 1 MGD and higher versus those that are below that 1 MGD, realizing that there are some technical challenges when you have small plants like that.
Yeah, and part of the biological nutrient removal or just the overall nitrogen and phosphorus removal that the IEPA is starting to enforce now, one of the light-ons in there is that as you do a study, it has to be feasible for your facility. They're not going to force you to do a multi-million-dollar project on a small plant just to control these. They'll target those higher reductions at other plants, or they'll start working with the agricultural facilities in the area to do some controls. Um, so they do take into account economics for plants. Okay. Unless there are a few more questions, we have reached our time. We would like to thank everyone for joining us today. Again, this webinar has been recorded and will also be on our website, and we are working with the EPA Energy Office to get the approval for CEU credits. As soon as we have that information, we will pass that along to you. So thank you everyone for joining us today, and have a great afternoon.